Let's see how to determine the number of expected signals in an NMR spectrum. And the best way to do this is just to do a lot of practice problems. And we'll start with methane. And methane has 4 protons in the same environment. Therefore, we say those 4 protons are chemically equivalent, and we would expect to see only one signal on our NMR spectrum. So for methane, we would expect to see one signal because all 4 protons are chemically equivalent. If we move on to propane, right, so this carbon right here has 2 protons on it, and these 2 protons are in the same environment. Therefore, they are chemically equivalent, and we would expect to see only one signal for these 2 protons. If we look at these protons over here, so let me go ahead and draw them in. So these methyl protons are in their own environment here, so we'd expect one signal for these methyl protons. But for a molecule like this, you need to think about symmetry. So if I draw a line right here, it's easy to see that these 3 protons are in the same environment as these, right? So really, we have 6 protons in the same environment. So these 6 protons are chemically equivalent, and we would expect to see one signal for all 6. So for propane, we would expect to see a total of 2 signals. All right, let's move on to this one, right? So let's draw on our protons here. So let's just go ahead and draw on all of them first. So we're drawing in all of the protons, right? So we have these methyl protons here, and then right here we have a proton on this carbon, and then we have all of these protons. So a lot of them. Let's focus in on the methyl protons first, right? So these methyl protons here are in their own environment, and that environment is the same as all of these methyl protons. They're all in the exact same environment. They're all right next to a carbon with a hydrogen on it. And so we would expect to see only one signal for all of these protons. So one signal for the magenta protons. All right, so again, think about symmetry. Think about the symmetry of this. And then if I look at this proton right here, right, this is in a different environment from the magenta protons, but it's in the same environment as this proton. So we'd expect one signal for these red protons here. So one signal for the red protons. So a total of 2 signals for the molecule. All right, let's do some more examples. So let's look at this one next. All right, so we have a carbon right here with 2 protons on it, and these 2 protons are in the same environment. They're chemically equivalent. These 2 protons are next to this oxygen here. We know oxygen is more electronegative than carbon, so oxygen is going to withdraw some electron density. And so these 2 protons are in a different environment from these 2 protons. These 2 protons right here, let me go ahead and change colors. These protons in red are further away from the oxygen, so they're in a different environment. So we'd expect one signal from the protons in red, and we would expect one signal from the protons in yellow. All right, we still have our methyl protons. Let me go ahead and draw those in. So we have 3 protons over here on this carbon. They're further away from the oxygen. They're in their own environment, right? They're chemically equivalent, so one signal expected for these protons. Finally, don't forget about the proton right here, the proton on the oxygen. So that's in its own environment, so we would expect one signal for that proton. So really a total, right, if you count them all up, a total of 4 signals, right? So we would expect 4 signals. Not sure why I put an S on here, only one signal. So a total of 4 for this alcohol. Let's look at this alcohol down here. So we have these 2 protons, right? And these protons over here, and these protons over here. So let's think about that. So symmetry helps for an example like this. These 2 protons, right, are in the same environment. They're between 2 CH2s, and so we'd expect one signal for these protons. So they're chemically equivalent. Let's look at these protons next. So these right here, right, are next to a CH2. They're also next to an OH. That's the exact same environment as these protons, right? They're next to a CH2 and next to an OH. So if you think about symmetry right here, we'd expect only one signal for these 4 protons. And then finally, we still have we have the proton on the oxygen. And once again, symmetry helps us think about the fact that this proton is in the same environment as this proton. So we would expect one signal there. So we would a total of 3 expected signals for this molecule. All right, let's move on to this compound over here on the right. And we can see that there's a chiral center right here on this carbon. And there therefore must be a hydrogen, a proton on that carbon. So let's go ahead and draw in all of our protons, and then let's analyze them here. So we have 3 protons on this carbon. On this carbon right here, we have 2 protons. Right? I'm drawing them in with a wedge and a dash because we're going to need to think about those 2 protons. And then over here, right, we have 3 like that. All right, so let's think about how many different signals we're going to get. All right, so in the past, let me go back and use a different color here. When we talked about a CH2 group, right, and we didn't have any chiral centers, like these 2 protons right here, we didn't have any chiral centers in this molecule. These 2 protons are generally equivalent. Right? But if I think about over here, I have a chiral center at this carbon, and that's going to affect these 2 protons. These 2 protons are no longer chemically equivalent, right? Because a chiral center is present. So in general, if a chiral center is present, the 2 protons on a methylene group, on a CH2 group, are generally not equivalent. So we would expect 2 different signals. So this one might give us 1 signal. I'll put that in magenta, so 1 signal here. And this one, we would expect a different signal. They're in slightly different environments because of this chiral center that is present. All right, so let's keep on going, and let's figure out how many more signals we would expect. So over here, right, we have these 3 protons are chemically equivalent, and they're in their own unique environment. So we would expect 1 signal for those 3 protons. All right, and those are in a different environment from these over here. So you would expect 1 signal for these. So for a methyl group, so methyl protons are always in the same environment, so they're chemically equivalent. So you don't have to worry about them. All right, and then let's see, what else do we have here? We have the proton on the oxygen, so we would expect 1 signal for that. And then finally, we're going to have, let's see, what color should I choose here? Let's go with orange. We still have a proton right here in its own unique environment, so we'd expect 1 signal for that proton. So how many total signals do we expect? So let's count them up. So 1, 2, 3, 4, 5, and 6. So a total of 6 expected signals for this alcohol. All right, let's move on to a benzene ring here. So let's look at benzene, and we know that benzene has 6 protons, right? So I could draw in the 6 protons here, and those 6 protons are all in the exact same environment. They're all chemically equivalent, and sometimes it's easier to just go ahead and draw your circle in here, right? And that just helps you to see that these protons are equivalent. It allows you to see the symmetry a little bit better, right? So again, thinking about symmetry, all 6 protons are in the same environment. Therefore, we would expect only 1 signal for benzene on an NMR spectrum. So let me go ahead and write that here. So only one signal for benzene because all 6 protons are chemically equivalent. Move over here to this molecule down here. All right, so let's think about what we have. So we have a methyl group here, a methyl group here. So that's 3 protons, right? So 3 protons for each methyl group. And those protons are in the same environment, right? So these 3 protons in this methyl group are in the same environment as these 3 protons, right? They're right next to an oxygen, which is next to this benzene ring. So next to an oxygen, next to a benzene ring. And so we'd expect only 1 signal, right? Only 1 signal for these 6 protons right here. If we look at our ring, we know that there's a proton here, we know there's a proton here, a proton here, and a proton here. And if we think about those protons, they're all in the exact same environment, right? So if I think about, let's say, this proton is next to a CH, right, with a double bond. It's next to a carbon right here with an oxygen. This is in the same environment as this one, right? This one's in the exact same environment. This one is. So again, symmetry helps you realize that all 4 protons are in the same environment, they're chemically equivalent, therefore one signal. So we would expect to see 2 signals. We would expect to see 2 signals for this molecule on an NMR spectrum. Finally, let's just, for fun, let's just look at cubane here, right? So one of the most interesting molecules, in my opinion. There are 8 protons on cubane. Cubane is just this this cube here, and those 8 protons are all equivalent, right? So if you think about, if you just rotated this cube, right, you wouldn't be able to tell a difference here. So we have 8 protons, all equivalent, therefore only one signal. So cubane's NMR should have only one signal on it. All right, so that's hopefully some insight into how to look at a dot structure and how to figure out how many signals you would expect to see on your NMR spectrum.